Dear students, today we'll discuss about additive manufacturing. This topic is actually the second part of your sixth module. The first half of this module is about micro machining, which we'll deal at a later stage. As of today, we'll have a very detailed discussion on different types of additive manufacturing techniques, the detailed steps involved in the manufacturing process and things. But before moving on, it is quite essential for us to understand what additive manufacturing is. If there is something like additive manufacturing, then there should definitely be something like subtractive manufacturing. Very true. We can classify manufacturing technologies broadly into three, namely subtractive manufacturing, formative manufacturing, and our additive manufacturing. With subtractive manufacturing, the desired geometry is obtained by removal of material. For example, by milling or turning. That's nothing but the conventional machining, what we have dealt in our previous semester subject, machine tools. Similarly, the formative manufacturing means it also alters the geometry in a defined way by applying external forces or heat. Say for example, by bending, forging, or even casting can be classified under formative manufacturing process. Formative manufacturing does not change the volume of the part. Now comes the additive manufacturing. Additive manufacturing creates the desired shape by adding material, preferably by staggering contoured layers on top of each other. Therefore, it is also called layer technology. Now, the term rapid prototyping is used in a variety of industries to describe a process for rapidly creating a system or part presentation before the final release or commercialization. There's a constant confusion between what is rapid prototyping and what is additive manufacturing. People tend to have a confusion between these two terms. Now, it is quite very important for us to understand if these terms are the same or is it different in literal sense. So let's have a look into it. Rapid prototyping, it's emphasized on creating something quickly and that the output is a prototype or basis model from which further models and eventually the final product will be derived. Even the management consultants and software engineers both use the term rapid prototyping to describe a process of developing business and software solutions in a piecewise fashion that allows clients to test ideas and provide feedback during the development process. Whereas in a product development context, the term rapid prototyping was used widely to describe technologies which created physical prototypes directly from digital data. Users of the rapid prototyping technology have come to realize that this term is quite inadequate. That is, the term rapid prototyping is quite inadequate and does not effectively describe more recent applications of the technology. Improvements in the quality of the output from these machines have meant that there is a much closer link to the final product. Many parts are in fact now directly manufactured in these machines, so it is not possible for us to label them just as prototypes. The term rapid prototyping also overlooks the principle of these technologies in that they all fabricate parts using an additive approach. A recently formed technical committee within the ASTM International agreed that the new terminology should be adopted. So they have understood that the term rapid prototyping is not now enough to incorporate all the advancements in the technologies that is happening in the manufacturing sector. While this is still under debate, recently adopted ASTM concern standards now use the term additive manufacturing instead of rapid prototyping. So frankly speaking, additive manufacturing is an advanced version of rapid prototyping and that is exclusively used for the manufacturing segment. It cannot now be used in the software industry or the managed by the management consultants or things like that. So I hope now it's quite clear for you what is the actual difference between additive manufacturing and rapid prototyping. Next, we'll also discuss about the different developments that led into advancements in additive manufacturing scenario. Additive manufacturing technology came about as a result of developments in a variety of different technology sectors. Like with many manufacturing technologies, improvements in computing power and reduction in mass storage costs paved the way for processing large amounts of data typical of modern 3D computer-aided design models with reasonable time frames. Nowadays, we have become quite accustomed to having powerful computers and other complex automated machines around us, and sometimes it may be difficult for us to imagine how the pioneers struggled to develop the very first additive manufacturing machine. Advancement in computers definitely showed the development towards the additive manufacturing scenario. Additive manufacturing takes full advantage of many of the important features of computer technology, both directly, that is in the additive manufacturing themselves, and indirectly also within the supporting technology like processing power, graphics capability, machine control, networking, integration. So all these advancements in the computer technology helped in improving the technologies associated with additive manufacturing as well. Now, aside from the computer technology, there are a number of other technologies that have developed along with the additive manufacturing that are worthy to note, since they also have contributed further improvements in additive manufacturing systems. Like we have the laser technologies, which is quite advancing, the printing technology, the materials, and also the advancement in CNC machines. So all these are actually contributing to the rapid growth of additive manufacturing processes. Moving on, we look into the different steps involved in additive manufacturing process. Additive manufacturing involves a number of steps that move from virtual CAD description to the physical resultant part. Different products will involve additive manufacturing in different ways and to different degrees. Small, relatively simple products may take only maybe that way additive manufacturing for visualization models, while larger and more complex products with greater engineering content may involve additive manufacturing during numerous stages and iterations throughout the development process. Furthermore, early stages of the product development process may only require the rough parts, with additive manufacturing being used because of the speed at which they can be fabricated. At later stages of the process, parts may require careful cleaning and post-processing before they can be used, with additive manufacturing being useful here because of the complexity of the form that they can be created without having to consider tooling. To summarize, most additive manufacturing process include the following 8 steps. Step 1 would be conceptualization and CAD. Step 2 would be conversion to STL file format. Step 3 is transfer to the additive manufacturing machine and STL file manipulation. Step 4 is machine setup. Step 5 is build, making your machine ready for the build up. Step 6 is the removal and cleanup. Step 7 is the post-processing processes. Step 8 is the application, the area where you are going to employ your part produced. Now, as an explanation to the first step, conceptualization and the CAD, all the additive manufacturing parts must start from a software model that fully describes the external geometry. This can involve the use of almost any professional CAD solid modeling softwares, like you might have learned already about SolidWorks and things, Unigraphics and other things. But the output must be a 3D solid or a surface representation. Reverse engineering equipment like laser scanning can also be used to create this representation. Now the second step is all about conversion into STL file format. Now let's see what is STL file format. Nearly every additive manufacturing technology uses the STL file format. The term STL was derived from stereolithography, which was first commercially available additive manufacturing technology from 3D systems in the 1990s. STL abbreviation also has the following expansion like standard tessellation language or standard triangle language. Considered a de facto standard, STL is a very simple way of describing a CAD model in terms of its geometry alone. It works by removing any construction data, modeling history, etc., and approximating the surfaces of the model with a series of triangular facets. Now the next step would be to transfer the STL file to the machine. Once the STL file has been created, it can be sent directly to the target additive manufacturing machine. Ideally, it should be possible to press a print button and the machine should build the part straight away. This is not usually the case, however, and there may be a number of actions required prior to the building the part. The first task would be to verify that the part is correct. Additive manufacturing system software normally has a visualization tool that allows the user to view and manipulate the part. It is quite common to build more than one part in an AM machine at a time. This may be multiples of the same part, thus requiring a copy function or completely different STL files. STL files can be linearly scaled quite easily. Some applications may require the AM part to be slightly larger or slightly smaller than the original to account for process shrinkage or coatings, and so scaling may be required prior to building. Now the fourth step is all about setting up the machine. So all the machines for additive manufacturing technology will have at least some setup parameters that are specific to that machine or the process. Some machines are only designed to run perhaps one or two different materials with no variation in layer thickness or other build-up parameters. These types of machines have very few setup changes to make from build to build. Other machines are designed to run with a variety of materials and may also have some parameters that require optimization to suit the type of part that is to be built, or permits parts to be built quicker but with poorer layer resolution. For example, such machines can have numerous setup options available. It is common in the more complex cases to have default settings or save files from previously defined setups to help speed up the machine setup process and to prevent mistakes being made. Normally, an incorrect setup procedure will result in a part being built. The final quality of the part may, however, be unacceptable. Now let's look into the fifth step, which is about building the part. Although benefiting from the assistance of the computers, the first few stages of additive manufacturing process are semi-automated tasks and that may require considerable manual control, interaction and decision making. Once these steps are completed, the process switches to the computer controlled building phase. This is where the previously mentioned layer-based manufacturing takes place. All the additive manufacturing machines will have a similar sequence of layer control using a height adjustable platform, material deposition and layer cross-section formation. Some machines will also combine the material deposition and layer formation simultaneously, while others will separate them. All machines will repeat the process until either the build is complete or there is no source material remaining. In either cases, the machine will alert the user to take action. Now, moving on to the sixth step. After you build the part must either be separated from a build platform on which the part was produced or removed from excess build material surrounding the part. Some additive manufacturing process use additional material other than that used to make the part itself. There is a degree of manual skill required, since mishandling of the parts and poor technique in support removal can result in a low quality output support materials. The cleanup stage may also be considered as an initial part of the post-processing stage. Now the seventh step is all about post-processing. Post-processing refers to the usually manual stages of finishing the parts for application purpose. This may involve abrasive finishing like polishing and sandpapering or application of coatings. This stage in the process is very application specific. Some applications may require a minimum of post-processing, taking advantage of the speed at which the parts are made. Other applications may require very careful handling of the parts to maintain good precision and finish. Different additive manufacturing processes have different results in terms of accuracy and material properties. Some properties produce relatively fragile components that may require the use of infiltration or surface coatings to strengthen the final part. As already stated, this is primarily a manual task due to the complexity of AM parts. However, some of the tasks can benefit from the use of power tools and additional equipment like polishing tubs or drying and baking ovens. Now the last step is about the applications. Following the post-processing, parts are ready for use now. It should be noted that although parts may be made from similar materials to those available from other manufacturing processes, parts may not behave according to the standard material specifications. Some additive manufacturing processes inherently create parts and small voids or bubbles trapped inside them, which could be the source of part failure under mechanical stress. In addition, some processes may cause the material to degrade during the build or for materials not to bond, link or crystallize in an optimum way. In almost every case, the properties are anisotropic. This may result in parts that behave differently than if they were made using a more conventional manufacturing approach. However, additive manufacturing materials and processes are improving all the time, and many applications do not require high performance and many of their components. The number of applications for the output from additive manufacturing is therefore constantly increasing. Now we'll move on to the different types of additive manufacturing techniques. We can broadly classify the additive manufacturing process into 4. The first one would be stereolithography, or you call it as SLA method. The second would be selective laser sintering, which can also be called as SLS method. And the third would be fused deposition modeling, or FDM method. And the fourth one would be laminated object manufacturing, LOM method. First, we'll have a discussion regarding the SLA method. Stereolithography, more commonly referred to as SLA 3D printing, is one of the most popular and widespread technologies in the world of additive manufacturing. It works by using a high-powered laser to harden liquid resin that is contained in a reservoir to create the desired 3D shape. In a nutshell, this process converts photosensitive liquid into 3D solid plastics in a layer-by-layer fashion using a low-power laser, and the process called is photopolymerization. SLA is actually the oldest additive manufacturing technique known. The technology and the term were created in 1986 by Chuck Hull, founder of 3D printing company 3D Systems. According to him, SLA is a method of creating 3D objects by successfully printing layers, by which he meant a photosensitive material. In 1992, 3D Systems created the world's first SLA apparatus, which made it possible to fabricate complex parts layer by layer in a fraction of the time it would normally take. SLA was the first entry into the rapid prototyping field during the 1980s and has continued to advance itself into a widely used technology. Every standard SLA 3D printer is generally composed of 4 primary sections. You will have a tank filled with a liquid photopolymer. The liquid resin is usually a clear and liquid plastic. A perforated platform immersed in a tank. The platform is lowered into the tank and can move up and down according to the printing process. A high-powered ultraviolet laser. A computer interface which manages both the platform and the laser movements. One alternative of SLA is the digital light processing, DLP. Unlike SLA, DLP uses a digital projector screen to flash a single image of each layer across the entire platform. As a projector is a digital screen, each layer will be composed of square pixels. Thus, the resolution of a DLP printer corresponds to the pixel size, whereas SLA is the laser spot size. For the better understanding, we'll see an animation showing the working of SLA machine, where you can clearly see how we have a tank wherein the photosensitive liquid resin is filled in it, and you can see how a laser is controlled to form a particular part. The next type is called the selective laser sintering or SLS. The SLS process was developed and patented in the 1980s by Carl Deckard. Like all the methods of 3D printing, an object printed with an SLS machine starts with a computer-aided design, that is a CAD file in the STL format, which can be understood by a 3D printing apparatus. Objects printed with SLS are made with powder materials, most commonly plastic such as nylon, which are dispersed in a thin layer on top of the build platform inside the SLS machine. A laser, which is controlled by a computer that tells it what object to print, pulses down on the platform, tracing a cross section of the object onto the powder. The laser heats the powder either to just below its boiling point, or it's also called as sintering temperature, or above its boiling point, which is called as the melting point, which fuses the particles in the powder together in a solid form. Once the initial layer is formed, the platform of the SLS machine drops, usually by less than 0.1 mm, exposing a new layer of powder for the laser to trace and fuse together. This process continues again and again until the entire object has been printed. While the object is fully formed, it is left to cool in the machine before being removed. Unlike other methods of 3D printing, SLS require very little additional tooling once an object is printed. It means that the objects don't usually have to be sanded or otherwise altered once they come out of SLS machine. SLS doesn't require the use of additional supports to hold an object together while it is being printed. Such supports are often necessary with other 3D printing methods such as SLA method or FDM method, making these methods more time consuming than when compared to SLS. SLS machines can print objects in a variety of materials such as plastic, glasses, ceramics and even metal. This makes it a popular process for creating both prototypes as well as the final products. Again, for a better understanding, let's see how SLS machine works. Next, we'll see about fuse deposition modeling. Let's see how this thing works exactly. Same as the other 3D printing machines, the FDM printer starts out with a CAD file, then it is being converted to STL file format. Now, the FDM printers use two kinds of materials: a modeling material which constitutes the finished object, and a supporting material which acts as a scaffolding to support the object as it is being printed. During printing, these materials take the form of plastic threads or filaments which are unwound from a coil and fed through an extrusion nozzle. The nozzle melts the filaments and extrudes them onto a base, sometimes called a build platform or table. Both the nozzle and the base are controlled by a computer that translates the dimensions of an object into X, Y, and Z coordinates of the nozzle and the base to follow during printing. In a typical FDM system, the extrusion nozzle moves over the build platform horizontally and vertically, drawing a cross-section of an object onto the platform. This thin layer of the plastic cools and hardens, immediately binding to the layer beneath it. Once the layer is completed, the base is lowered, usually by about 1/16th of an inch, to make room for the next layer of plastic. Printing time depends on the size of the object being manufactured. Small objects, it just take a few cubic inches and tall, then objects prints quickly, while larger, more geometrically complex objects takes longer to print. Compared to other 3D printing methods such as SLA and SLS method, FDM is fairly a slow process. Once an object comes off the FDM printer, its support materials are removed either by soaking the object in a water and detergent solution, or in case of thermoplastic supports, snapping the support material off by hand. Objects may be sanded, milled, painted, or plated to improve their functions and appearance. FDM is popular with companies in a variety of industry, from automotive to consumer good manufacturing companies. Companies like BMW, Hyundai, Lamborghini, and consumer good manufacturing companies like Black & Decker, Dial, and Nestle uses these technologies throughout their product development, prototyping, and manufacturing process. The most common printing material used for FDM is ABS, which is nothing but acrylonitrile butadiene styrene, a very common thermoplastic available. And the best example would be the Lego bricks, with which usually the kids play with. Now, for a better understanding, a small demonstration is shown here. One other type of additive manufacturing method is known as the laminated object modeling, or LOM as it is known. An LOM apparatus uses a continuous sheet of material, plastic, paper, or metal even, which is drawn across a platform by a system of feed rollers. Plastic and paper build materials are often coated with an adhesive to form an object. A heated roller is passed over the sheet of material on the build platform, melting its adhesive and pressing it onto the platform. A computer controlled laser or blade then cuts off the material into the desired pattern. The laser also slices up any excess material in a crosshatch pattern, making it easier to remove once the object is fully printed. After one layer of the object is formed, the build platform is lowered again by about 1/16 of an inch, the typical thickness of one layer. New material is then pulled across the platform, and then the heated roller again passes over the material, binding the new layer to one beneath it. The process is repeated until the entire object has been formed. Once an object is done printing, it is removed from build platform and any excess material is cut away. Objects printed in paper take on wood-like properties and can be sanded or finished accordingly. Paper objects are usually sealed with a paint or a lacquer to keep out the moisture. The first LOM rapid prototyping system was developed by the company called as Helicis. Helicis is a very big company and a very known company, just like the other company called as Stratasys. Cubic Technologies now sells services and supports Helicis products. For better clarity, let's see an animation. So dear students, I hope you understood the basic concepts of additive manufacturing. We also explained its types. It's one of the emerging areas in the manufacturing world. Machines capable of producing metal part directly from metal powders are now commercially available in the market. This concept is the next big thing, no doubt in it, and it completely promotes the Industry 4.0 revolution. Research and developments are still going on to make it more affordable as well as to make it more versatile. Hope you had a very good session. Thank you for the patience and have a very good day.